All right. Okay, so make sure everything's working. It appears to be right on. Okay, so today we are continuing our conversations that we were having about proportional reasoning from last week. We do technically have three more lessons to get through. And area and volume are related in a number of ways. So I'm imagining that we will probably go um, through two of those lessons, maybe only one of those lessons tomorrow. The reason I haven't sent out like the full weekly schedule, we'll meet the same time tomorrow. So it'll be physical science at 2. Um, I think I'll send out a confirmation of that, but I think physical science either at 2 or 1. I'm not entirely sure. And then 2:30 will be I think math or 1:30. Again, I'll send out a confirmation of that right after this lesson here. But I want to go through a couple of these. The reason that I haven't sent the schedule out is Mr. D asked me to take a picture of us, quote unquote, in class and to use that for the yearbook. So I'm going to send out a survey and also probably a Zoom meeting link, and then we'll just do the lesson on Zoom tomorrow. But I will confirm all of those details and just make sure that I've got everything hammered out before Tuesday or Wednesday or whenever we happen to do that. But jumping into scale diagrams, we have a couple blanks that we need to fill in to start this off. When two objects are the same, but one is an enlargement or reduction of the other, the objects are called similar. Similar is the term that we want to use. And then we're going to be referring to them as scale diagrams. So, what scale diagrams refers to as looking at two things. One of them is a scaled down version of what the actual thing or the actual size is. I thought it was kind of interesting when I was doing some research earlier this morning. I found out that this statement, so identical shapes are congruent. So we don't want to use the word congruent when we're describing these shapes because they are not identical. They are scaled diagrams of each other. So one of them is bigger or smaller than the other. And the main formula that we're going to be using is this one here. This scale factor is equal to diagram measurement, so the size of whatever has been drawn divided by the actual measurement. The diagram is an enlargement of the original shape if the scale factor is greater than 1. And the diagram is a reduction of the original shape if the scale factor is smaller than 1. Now, I didn't put is equal to 1. And the reason I didn't put equal to 1 is that if they had a scale factor which is k, if they had a k of 1, they would be congruent. So they would neither be an enlargement or a reduction, but they would be actual congruent. They would be the same shape. And there would be no reason for us to ever talk about the scale factor of those if in fact it was the exact same size, the drawing as the actual object or whatever we're comparing. So we actually did this a few times last semester in health sciences. But example number 1 says the diameter of an animal cell that is represented by this scale diagram, the actual size of it is 0.25 millimeters. And so the question that we're asked then is what scale factor was used to draw the scale diagram? Now, the first thing that we need to do is we need to get our units to be identical. And so what I'm going to do is I'm going to take 0.25 millimeters and I'm going to convert that into centimeters. So for every millimeter, for every 10 millimeters is 1 centimeter. So you end up with 0.025 centimeters. And then based on this formula above, how we want to calculate the scale factor is we want to take the diagram's measurement, which was 3.5 centimeters, and we want to divide that by the actual measurement, which was 0.025 centimeters. Now, when I was working through these questions earlier in the day, just going over them and making my own little notes, what I often did when I looked at these questions is I tried to use a little bit of common sense when looking at these, saying, okay, this drawing is 3.5 centimeters here. The actual thing was 0.25 millimeters. It was a very, very small cell. And so I'm guessing that this thing has been magnified magnified or enlarged, meaning I should have a scale factor that's bigger than 1. So if all of a sudden I screwed up when I was doing my math and I got a scale factor that was smaller than 1, that would alert me that, okay, I've probably done something wrong. So when I'm doing this question, that's the background of what's going on in my brain, is me saying, okay, it needs to be within this region. It needs to be bigger than 1. Otherwise, I screwed up somewhere. And in fact, when you do this, you get a magnification of 140 times. And so the scale factor, or K, would be 140. Just kind of a point of interest. I was playing board games with some friends, and it is a game where you try to. It's kind of like Codenames in a way, but you're trying to figure out the murder weapon and also what was left at the scene of the crime. And one of the murder weapons was actually an amoeba, which I thought was kind of fascinating, because amoebas, that would be very tough to kill somebody with an amoeba. But we did some research into it, and we actually found out that amoebas can grow up to 20 centimeters in size. And most of the way that they kill you is usually in the ocean. They will sneak in through your ear or through another hole on your face, and they will start to eat your brain. And that is one of the ways that an amoeba can kill you. So I just thought that was kind of interesting. Back to the original question, which says, is this an enlargement or a reduction? We know, in fact, that 0.25 millimeters, that's a lot smaller than 3.5 centimeters. So we would describe this as an enlargement. This has gotten bigger. The other key was that we found that we had a 140 scale factor, which also means that it's an enlargement. This second example here, the key instruction here is identify which of the following objects are similar. So the idea is that this is the exact same object, but it's been quote unquote scaled up. So it's been made bigger than what the original object was. Now, when I was looking at these questions, how I liked to compare these was I like to take two of the exact same side, pair them up, and see what the ratio of those is. So I like to use the ratio or the fraction to compare and see if this was in fact similar objects. So what I would do then is I would do 4 divided by 6. And when I did that, I got 0.6 repeating. And so what I would then say is I would say, if these two objects are actually similar, whenever I take other of the same size, of the same side, those two better have the exact same ratio, or they better have the same decimal value. Because if they do, then I know that these things have been scaled up or scaled down by 0.6. So I know that if I wanted to go from this right object here, I would have to multiply each of those numbers by 0.6 repeating. And so what I did when I was going through this is I did 3 divided by 4.5, and I also found 0.6 repeating. And then I did 5 divided by 7.5, and I also found 0.6 repeating. And so as such, I can conclude that because each of these measurements have been scaled up in the exact same way, that yes, those two objects are similar. Some of the questions, like this second one here, become very, very obvious that they are not the same object, or they are not similar objects. For example, we have 5s on each of those measurements. So a length of 5, length of 5, length of 5. We have an equilateral triangle. And yet when we come over here, we still see an equal length of 5. So we would expect, well, if these two objects are congruent, then we would expect a 5, a 5, and a 5 on all three sides. But we don't see that. We see a 6.5 and we see a 6.5. So immediately, just looking at this, I can say that not all side lengths have been scaled up or scaled down the same. That this DF side length of 5, that remained the same. It wasn't scaled up at all. So right away, I know that those two objects are not similar. Looking at the Coca-Cola example here, we have measurements. We have a width there of 2. We have a height of 4. And then on the second one, we have a width of 2.5, and we have a height of 5 inches. And so again, what I would do is I would take that length and that length, since they're both measuring the same thing on the Coke cans, and I would create a decimal for the blacks. and create a decimal for the blues. And when I do 2 divided by 2.5, you end up getting a decimal of 0.8, of 0.8. And so then what I do is I check and say, well, okay, what's 4 divided by 5? It's also 0.8. Those are the exact same. Awesome. I can say that, yes, those two objects are similar because they've been scaled up or scaled down the exact same. And that's told to me by this decimal. So all I'm doing with these questions, there's one last one that we'll get to. All I'm doing with these questions is using this scale factor formula. But what I'm doing is I'm saying I don't really care if I put the smaller one up top or the bigger one up top. I could also compare them like this. I could also say 2.5 divided by 2 is equal to 1.25. And then I could look at this and say 5 divided by 4. That's also 1.25. Awesome. I know that those two are similar objects as well. This decimal value or this scale factor that we're figuring out, that communicates a lot of information to us. And because those two are the same, we know that this is, in fact, a similar object. When we look at this last example, I'll show you what happens when it is not the same. So we have a house that has dimensions of 12 by 9. So we're going to assume that this is a two-dimensional house with dimensions of 12 by 9. And then the blueprint here has dimensions of 24 centimeters by 9 centimeters. And so I know many of you would be 19 centimeters is what that should be. Many of you would see this and say, that's no good. We need something with the identical units. We need something with meters. So we'll look at two different examples. I am going to convert them to meters. And to do so, there are 100 centimeters in 1 meter. So I know that this would be 0.24 and this would be 0.19. And what I want to do then is I want to take these two measurements here and I want to take these two measurements here and I want to compare those and see if they are in fact identical. So when I go 9 divided by 0.19, I get an answer of 47.3. And then for the greens, I go 12 divided by 0.24. And when I do, I get an answer of 50. And so what that tells me is that tells me that those two objects are not in fact similar because they have been scaled up differently. So the blueprint had 24 centimeters by 19 centimeters. And when it was scaled up and actually built, we found that the actual width, the 9 meters here, was actually a little lacking in comparison to the 12 meters. Now, what I wanted to show you as well is I wanted to show you what would happen if you didn't convert between units. So let's say that we did 9 divided by 19. Let's just draw a line here. And the other option that we had was 12 divided by 24. Those are the two answers that you end up getting. You get a 0.473 and a 0.50. And what you'll notice is something very interesting, that these decimal values are 100 times less than these decimal values. If I took 40.473 and multiplied by 100, I would end up with 47.3. So when we're comparing, we don't actually need to necessarily have the same units. We don't need to communicate and have the same units as long as all of the one diagram is in the same units. So what I mean by that is as long as every measurement in this diagram is in centimeters, that's awesome. We're fine. And as long as every measurement in this is meters, then we're also fine. Where we can run into issues is, let's say that I only converted this 24 centimeters into 0.24 meters. That's where our scale factor will run into some issues because then we would have been comparing a 47 point, we would have been comparing a 0.473 to a 50. Well, those two are clearly off, and that would be a result of our units being wrong. Moral of the story, kind of the summary of what I'm saying, in one diagram, have all the same units. So in the blueprint, have it all centimeters or all meters. In the house, have it all meters or all centimeters. Don't have mixed units in one object. All right. Does anyone have any questions so far? Okay, awesome. Example number 3 here. Jess designed the logo for an environment club. She wants to enlarge the logo so that it can be applied to the front of the baseball cap. And the hat company has suggested a scale factor of 5:3. So the question here is, will the logo on the hat be bigger or smaller than the logo shown here? They've recommended a scale factor of 5:3. And the key sentences that we had said earlier was that if our scale factor was bigger than 1, it's an enlargement. If our scale factor was smaller than 1, we have a reduction. That was these two sentences here. And then if we said it was equal to 1, that was a congruent, not a similar shape. So what I would do here is very quickly look at 5/3 and say, is that bigger or is that smaller than 1? And if you are someone that does not like fractions, you could convert that to a decimal by going 5 divided by 3. You get 1.6. And so what that means is because this is greater than 1, this will be an enlargement. This will be bigger than the logo shown. Enlargement, like such. The next question was, what would the dimensions of the logo that would appear on the baseball cap? If we were in the classroom, I'd have you measure this with a ruler. Because we're not, that's how big the logo is. It's 5 centimeters drawn on your page. So the question is, what would the dimensions of the logo be that would appear on the baseball cap? Well, we know that we want to enlarge it by 1.6 times. And the way I'm saying that is important. I want to enlarge it by 1.6 times, or 5/3 times. And so the two ways that you could solve for this is you could go 5 times 5/3, or you could go 5 times 1.6 repeating. Either way, you get the exact same answer, which is 8.3 repeating centimeters. I should have included centimeters here. So the logo on this hat would be 8.3 centimeters, which is a pretty large logo for hats. Okay. Example number 4 here says a toy vehicle is made at a scale of 1 to 64. 1 to 64. What would the real dimensions of the car be if the real car itself, so I'm going to draw a really, really bad boxy car. We'll call it the Nissan Cube. Nissan Cube. Like that. Here are the little wheels. Nissan Cube is not a very good looking car. But it was 4.5 meters long, so this side length is 4.5 meters. It's 1.65 meters high, and it's 1.82 meters wide. And this should be this value here. This value is 1.82 meters, like such. So, toy vehicle is made at a scale of 1 to 64. What would the real dimensions be? So, we can think of these ratios as well. Is we can think of those as fractions as well. We could think of that ratio as 1/64th of the size, or we could think of the car being 64 times bigger than the actual toy vehicle itself. And so what I'm going to do with these values is, because I have the actual car value, we know that this is the car and then this is the toy. That the car is going to be 64 times bigger than the actual toy would be. And so what would make sense then is we need to take 1/64th or multiply by 1/64 for each of the values that we were given of the car. So I'm going to do that. 1.65 meters times 1/64, and 4.5 times 1/64, like such. I'm going to take each of these values and divide by 64, or multiply by 1/64. So when you do this one, you get a value of 82 divided by 64. You get a value of 0.02 2.8 meters. This one you get a value of 0.0226 meters. This last one you get a value of 0.07 meters. I didn't love these answers when I was going through it. So what I did is I said, well, I know that for every 1 meter, there's 100 centimeters. So I just multiplied all these values by 100 and converted them instead into centimeters. So this was 2.8 centimeters, this was 2.6 centimeters, and this was 7 centimeters. Were the final answers that we ended up with. So the real car would have, or the toy car, excuse me, would have a length of 7 centimeters. It would have a height of 2.6 meters and would have a width of 2.8 centimeters. Last example below. Key little sentence here is this says the two shapes below are similar. So we've already been told that they're similar. We don't need to conclude or try and figure out or decide if they are similar. What we do need to do, though, is we need to look at these two triangles and figure out what side corresponds to what side. And the way that I did that is I looked at these two triangles and I said, okay, we have this angle and this angle here that are equal to one another. Each little line tells you this is angle 1 equal to angle 1. So this little angle here is equal to this little angle here. This angle with the double is equal to the double. The triple is equal to the triple. And so what I did is I said, okay, let's look between the two different angles and see what side length exists. And so between 1 and 3, we have 36. And between 1 and 3, we have 24. So I know that those two are linked together. Next thing I did is I looked at between 1 and 2. And I see 33 centimeters. And then between 1 and 2, I see a y. So that's one thing that I'll have to solve for with this little red here. And then with the blue, I like to use different colors just so I can easily pick which side is linked to which. The only two sides left, though, are those two there. All right. So looking at this, we have two different side lengths on different triangles and with different colors to solve for. But we do have two side lengths that we know that are related to one another. We have two similar side lengths. So what I did here is I said, well, okay, let's take 24, divide by 36, and let's figure out the scale factor. And when I did, I figured out that this is 0.727, and the 27 is repeating. So that's my scale factor between the two different triangles. So if I want to go from big triangle into small triangle, I'll write this below. Big triangle into small triangle. I want to multiply by this number. Because what that'll do is it'll take me from the bigger number into the smaller number. If we looked at this number and said, is this, what kind of scale diagram is this, or what kind of scale factor is this? We would say that this would be a reduction. Oh, I do too. I don't know where 0.727 came from. Thanks, Gene. I don't know where that number came from. I did that earlier, I guess. 0.6. That's much easier than 0.7. Thanks, Gene. Let's only do 2 6s there. Let's fix that. Okay, 0.66. Yeah, I don't know where that number came from. Anyways, not important. So 0.66, that's our scale factor. So what I want to do now is I want to look at the reds. And I want to say, I know that the one red length is 33 centimeters. And I said that if I want to get it to be smaller, I want to multiply by this 0.66. And when you do, you end up finding out that that side length there is 49.5 centimeters, which is not correct. What did I do? Oh, I did divide it. That's why. 3 times 0.66. and you end up getting 21.999, which I'm just going to convert into 22 centimeters. So just in case that wasn't clear, I made a mistake on my calculator. I accidentally hit divide. And when I did, I ended up getting 49.5. And just as a problem solving trick for you doing math, I saw the 49.5 was bigger than this 33. And I said, yeah, I did something wrong there. There's no way that a smaller triangle has a bigger side length when I know that these are the exact same triangle. There's no way that's possible. So for me, my problem solving was okay, I messed up somewhere. Let's figure out where I made a mistake. And I looked at my calculator and saw that I had divided instead of multiplying. So, just as a little trick for you, that was my mistake that I had made. Okay, now we get an interesting scenario with our blues left over. Previously, we had said that if we wanted to go from big triangle to small triangle, we would take whatever the blue triangle was and we would multiply by 0.66 and we would end up getting whatever our answer was. However, we know what this answer already is. We know that this answer is going to be 20 centimeters. So, what I would do instead is you could algebraically solve this and you could divide by the 0.66. Or you could say, well, if I had to multiply to get from big triangle to small triangle, I should have to do the opposite of that to get from small triangle to big triangle. So, if going small into big, we should divide by k. So what I'm going to do here then is I'm going to take my 20 centimeters and I'm going to divide by 0.66. And when you do so, you end up getting an answer of 30 centimeters. And that makes sense because that is bigger than this other side length. So this was 30 centimeters. And the last one here was 22 centimeters, like such. All right.